Okay, let me just get back to this pumice just for 1 second because it's pretty awesome. I had this picture too. This is side of a volcano. Geez, I believe that this is in Alaska. I think this is called Valley of 10,000 Smokes, which is an awesome name. In Alaska, this is a volcano, and you see all of these are chunks of pumice that from the eruption of this volcano, and I'm suggesting they're probably the size of your fist and bigger. So I really like seeing it in the real world, not just some rock on its own. So this is how it will form. In this case, probably like lava getting shot into the air and then cooling and hitting the ground, which is also awesome. Okay, so now we're going on to if it takes a little bit longer to cool. We're still on lava here. So if that lava on the surface of Earth will cool quickly, and quickly in this case is days to months, you have a thick lava flow that's 150 feet thick, the middle of that's going to take some time to cool. It may take months to cool. What you're going to get is a fine texture, which means the mineral crystals in that rock are going to be fine, really small. You won't be able to see them with the naked eye. Okay, they can't be seen with the naked eye. If you have this sheet of paper, they're smaller than that. I made that size on there very exact. So they are really small. They form on Earth's surface. They're volcanic. These are called extrusive igneous rocks. So let's get an example of this. Doesn't look like much when you look at it. This is igneous, fine texture. Crystals are too small to see with the naked eye. This is kind of a pinkish rock. And I have a close-up? No, I don't have a close-up. This is also igneous fine texture where the crystals are too small to see with the naked eye. The only way to see the crystals being angular interlocking crystals in a rock like this is you need to see it through a microscope, which you can do with a rock. Think about how microscopes work. Microscopes work with you put the slide on the stage and there's a light there, and the light is at the bottom. It shines through what's on the glass slide. So how are we going to look through a rock like this, get light to shine through a rock like this? Seems kind of impossible. But you can. You got to cut it really thin, really thin, really thin. And when you do that, and then you polarize the light, there's a little more to it, it'll look like this. So this is an igneous rock seen through a microscope. This is the angular interlocking minerals. And here you see the minerals of different color, the white minerals here and the light gray and black. You know, there's micas here. These are angular interlocking, which is cool. Here, wait, I have another one. This too, igneous rock. Now, you can see they're angular interlocking from that lava that cooled, and this is how they are formed. All the crystals are formed. Again, angular interlocking, and they are randomly placed. There's random order. There's no order to them. That's going to come into play. And I know that these are micas here, and then these minerals are those are the stripes are plagioclase feldspar. Totally cool with the stripes in there. If you know the New York reference tables have striations visible. Now, you're kind of filtering the light. There's some filters in the light. So it's a little more than just looking at a microscope, but very cool. Let me just go back to this then. So that's also extrusive. If it cools slowly, now we're getting into this, what we're going to call slowly. We're talking tens of years or more than that, so a long time for it to cool. Usually, this is going to be underground now. This is going to be that magma that never reaches the surface. You're going to have a coarse texture, which means the minerals are pretty large. And by large, we mean, I use the general rule of thumb that I use. If you can see it with your naked eye, mineral crystals, we call that large. It took a long time to cool. And the size of the crystals are usually like less, up to a centimeter is what we call coarse. So a centimeter, while pretty small, for a mineral crystal, rocks have mineral crystals of that size. That's coarse texture. Granite gabbro is an example of it. Again, if you can see it with the naked eye, we call that coarse texture. Okay, granite. So granite is something, to probably phrase you're common with the type of rock. Unfortunately, in the real world, people kind of call all a huge amount of a variety of rocks. They all call it granite if you're getting countertops. But in the real world of rock, there's specific rock that is granite, and this is a good example of it. If I look closer, angular interlocking crystals. Okay, may not really jump out at you, but they're all interlocking here, and you see that there's like black hornblende and some, well, you can't really see the mica. There's quartz, there's potassium feldspar, is like the pink is the potassium feldspar. The whitish or like grayish, the whitish is the plagioclase feldspar. The quartz is seen as clear here, or colorless. And so this is granite. So for instance, this keyword, not an igneous rock. And I can tell it's not an igneous rock because I have a close-up of it. You have rounded pieces, and this is all cemented together. This is all cement that keeps these rounded pieces together. So this is a sedimentary rock, and again, this is, I put this in there because it's an example of what rock is like when it's not angular interlocking mineral crystals that are randomly placed. Here's another one, not an igneous rock. Now, these are angular pieces, but this is all cement. The darker material here is all cement that holds those pieces together. Okay, so it's the lack of interlocking mineral crystals, again, cemented. So, as somebody's telling them apart, it takes some skill. Here's another one. This is diorite. Now, here you see a good mix of light-colored mineral and dark-colored mineral. If you look up close, hopefully you can see angular interlocking mineral crystals that are random. There's no pattern, no order, no layers to it. Okay, this is the igneous rock chart. Okay, what scientists do is they make charts or they make some sort of ordering system so we could make some sort of sense or study whatever it is we're studying. In this case, igneous rocks. This is the classic igneous rock chart, and there's a lot to it. It has the rock, has all the rock names up here, and then they're listed sort of by their texture: glassy, fine, coarse, very coarse. So they cooled from slow to, they cooled fast to slow. Okay, so you have that. The size of the mineral crystals generally get larger, and then what you have is like these minerals over here. These rocks. These rocks over here are similar in composition. They have similar minerals. We say they're felsic, which means they're rich in minerals that have a lot of silicon and aluminum in them. And this side, these are the darker rocks, and they're called mafic, so they have more iron and magnesium in them, which make them darker. And then here, it has this really cool chart that shows the mineral percentages, which I'm not really going to get into, but what I do want to do is show this, because what I did, I really like to see this. I put some of the actual rocks on the chart itself. So what you have here, and hopefully you can see it in real life, like these are lighter color, and obsidian is kind of an exception here because it's glassy texture. You don't really see the color really, but these are lighter colors. You're really going to see this granite, pegmatite, light colors here. The middle, as we go this way, it gets darker. The middle sort of intermediate because it's gray or this black and white diorite. And then over here you have the darker rocks. Again, more iron, more magnesium. Those minerals are darker, cause them to be darker. These more silicon, aluminum. These are more like quartz and the feldspars and these rocks. So that's how this chart is set up. In addition to glassy, these are, I don't know how well you can see this coming through on the video. These are vesicular texture because they take longer to cool. Fine grain, can't see the mineral crystals in this next layer. Now we're getting into coarse. Now you can probably see the different minerals at least by different color. Here, maybe not here. Here you can see them black and white. Here they're all dark, a little hard to see, but they are, if you had them in your hand, you'd be able to see. And this, probably a little hard to tell. This is even bigger crystals. This is a pegmatite. This took thousands and thousands of years to cool into hundreds of thousands of years to cool, so deep underground, which is really hard to wrap your brain around. But these crystals can get quite large. I'm not sure if you see that here so much. But so we have that going on, and then it relates to the bottom part of the table, which will actually tell you what minerals make it up and the percentage of the minerals, which is cool. I'm not going to get into those right now here in this video, but it is cool.